So we've got the alternate after each call, fixed runtime, and equal runtime. It's going to be the exact same rules that you're already used to on this. So when we talk about the new inputs, here is our I/O sheet. This would come packaged in the box with the controller. This has also been updated. I actually just grabbed this out of our Dropbox last night. And you'll see over here where I've got modulating boiler stage 1, modulating boiler stage 2. Okay, this is specifically the I/O identification for if you're choosing the modulating boiler setup in there. Okay, we still have our staged boilers up to 4 stages. We can do staged with valve in there if we need to. We have a separate I/O descriptor for that. So this is the M2000 hardware. This is the C1000. We can see here's our modulating boiler output. This output 3 is going to be our modulating boiler enable. And then we'll take over with the analog signal. And then I have my backup boiler stage. So that's the hardware side of it. Let's just go into focus here. Let me switch screens. And here we are. So I've already got my boiler controller in. We'll just open this up. And this is going to be a boiler feature. So we click on our boiler, and up here at boiler type, we will see our staging boiler. Here's the staging with valve, and now with our modulating boiler, I have the ability to choose my number of boilers. I can have a single, or I can have 2, okay? Same minimum on and off times, interstage activation delays on that. Here's your lead lag rotation. You guys are familiar with this drop down already, okay? Remind you that equal runtime does require the call to satisfy, so we need that boiler to shut down before we're going to rotate. If you end up in a situation where that boiler is going to fire and just run for days or weeks or months even, you know, perhaps you want to have it rotate based on a fixed runtime on there. We also have our backup boiler. So if we get, in this case, 9 degrees behind, we are going to fire up this digital output 4. Okay, so modulating boiler gets its own proportional, gets its own integral, and then we can choose our 0 to 10, 2 to 10, or 0 to 5 command signal. We have a minimum demand. Okay, we're not going to authorize that boiler with our enable until we reach at least 25% demand in this case. And once we get down to 15% demand, we're just going to shut it down. Okay, of course, many of our modulating boilers have a minimum firing rate, so we can adjust these levels to whatever is appropriate for that particular boiler. Okay, that's about it on adding the modulating boiler controls. So we'll go back over to the other screen. Here we go. Hi. Excuse me 1 second while I figure out how to drive this. Okay. So new features on the thermostat. This is a T1100. New sequence is discharge air control. As you're aware, that T1100 has a auxiliary temperature input on the back, so you could do a remote temperature sensing on that. Well, we can now put a duct temperature sensor into that auxiliary input on the back of the T1100, and we can use it for discharge air control. If you've used our makeup air controller with discharge air based on demand, this is going to work a lot in the same way. So I'm going to be able to reset the discharge set point based on zone demand, or I can have it really only function with a heating logic, and If we move to a cooling demand, we'll just change to maintaining a low limit on there. Thought process on this is for preheat coils. In cold climates, sometimes we will temper the air coming in before it even goes through the unit. We'll come from the outside through the damper and straight into a preheat coil before we even mix with the return. And that's kind of where we're looking at going with this. So back over to focus, and here is our thermostat. So same thing with the graphics, nothing's going to change here, but if we go into our outputs, either the digital or the analog, many times this will be an analog though, we can use a digital in it, and it can modulate with a pulse width modulation if you're doing electric heat and it's a triac or SCR. What we will do though is on this output source, instead of basing off of zone demand, what we're going to do is change to discharge air control. Actually, I forgot to show you on this. What we're talking about is, let me get back to it here. Right here on our input, so we've got this auxiliary input here, is going to be a 10K type 3, just as with any other temperature in ProLon. Okay, so that's just going to connect to the aux in, and that will go into the duct. The T1100 is then going to focus on controlling that off of demand. So back to the setup on this. Here we are. So we choose our discharge air control. We can use a heating or cooling. Typically, it's going to be a heating logic. And this is where our controller generating that demand, whether it is minus 100 is a full cooling demand, plus 100 is a full heating demand, 0 is satisfied. So you can see how we will, in a full cooling demand, we will have a lower discharge air set point. In a full heating demand, we'll have a higher set point, all of these numbers adjustable. And with 0 demand, we're going to target fairly neutral air. We also have the ability on this to deactivate on a call for cooling. So basically, we'll do our temperature reset through the heating demand, but upon a call for cooling, we're just going to drop into a low limit maintenance there. We'll catch it at 55.4 is our factory default on this. And then again, we have our choices with the analog output, 0 to 10, 2 to 10, 0 to 5. If we had the digital output on this, it would be operating with a pulse width modulation as if we had checked the pulse box here. Okay, so that is it on the T1100. Let me get us back over to this screen. And next we have the rooftop. Okay, so dehumidification has been a little bit of a sticking point with the rooftop, because what we had to do previously is use the master version, the RTU, which then required us to use, if it was a single zone, we had to have a T1100, and then we also had to have the C1000 humidity controller. Okay, so when we're just trying to do dehumidification, you know, that's a lot of equipment to purchase, and that can make our cost a little excessive. The C1000 is no longer required. Okay, now because of the necessary I/O on this, the this is only available on the M2000 hardware platform. Okay, we will be able to add a %RH transducer. It'll be scaled 0 to 100% over 0 to 5 volts, and that will go directly into one of our inputs that we can now repurpose. It's a dual function input. When I take a look at this on my I/O diagram, okay, over here, input 6, that used to only be my zone temperature set point 10K potentiometer if I chose to use that. Now we also have the option of that being a zone humidity sensor. Many times, this input 5 and input 6 are sitting empty because of a communicating wall module, or it's a master control, and so it's getting its demand by averaging zones. So we don't normally use inputs 5 or even more rare input 6. So that's why we chose to stick it there. Just a note, if you do have to change this, if you are going to use the dehumidification, you will need to open up the M2000 and change the input type jumper, okay, from resistive over to a voltage on that. So let's take a look at focus on this again. Okay, so with our rooftop, previously, this is our single zone rooftop. We'll go ahead and do our usual dressing this, getting rid of our bypass damper on there. So here's our single zone rooftop. Remember, this is a slave device. Okay, so it does not have the ability to talk to a C1000 if it wanted to. Because of that whole master-slave relationship, two slaves can't chat with each other. A slave can only talk to a master. That's why we had to use the RTU version. I'll show you that in just a sec. But now down here, config dehumidification. Source of dehumidification demand, well, I can have none, or I can do analog input 6, which I just showed you on the diagram. So this will allow us to stage into cooling, okay, based off of humidity. So stage 1, stage 2, or we can get into economizer based on if we have an enable set point on that outside. Now remember, dehumidification is a secondary operation to our comfort heating and cooling. So note down here that the dehumidification demand will be deactivated as soon as there is a cooling or heating demand strong enough to activate the equipment using the normal set points. Okay, so keep that in mind. Now, part of dehumidification is it does allow for preheating. So we would hope that this unit has a preheat coil in there. That way I can run with my cooling and preheat at the same time. If I don't have preheat available, what will happen is basically we are going to overcool using our dehumidification demand. And when we overcool there, of course, eventually we're going to reach a point where we start producing a heating demand. So ideal situation, we're going to have a preheat available on this, and we'll be able to kind of drive with our foot on the gas and the brake at the same time to wring that humidity out. If we go up to the rooftop, you know, as you're well aware, at ProLon, we do not like to remove any features. So this rooftop is still perfectly capable of using a C1000 humidity controller, and they can communicate through the network just as usual. Or here we can choose to use that analog input 6. So everything about this is going to be exactly the same. The difference is I just have the option to use a C1000 as my input source for humidity. All right. So moving on, back over to the other screen. All right, makeup air. So not a huge change on this. Still going to have our discharge air temperature reset based on zone demand or outside air temperature. But as you may recall, previously we had a single analog output, but it was a staged output. It would only give 0 volts, 5 volts, or 10 volts DC on that. 5 volts was first stage, 10 volts was second stage. And that was it. There was no way that we could ramp that up and down, but that was not a hardware limitation. That was just a software limitation. So we have now added full modulating capability. We're still going to be talking about the same output here with this AO2. That will be our cooling. It will still give our staged if we want, the 0, 5, or 10, or we can treat it as a full analog and drive a chilled water valve or whatever analog cooling source we might have there. So to take a look at that, I'm clicking as fast as I can. Here we go. Here's our makeup air controller. When we set up our hardware on this, we're going to choose with our mechanical cooling, is it going to be staged? Okay, so this is the previous operation that we had. We can have 1 or 2 stages on that, or is it going to be analog? Okay, choose our range on this, 0 to 10 or 2 to 10 volts DC. Once we have that, when we go see our summer configuration, we now have the same discharge air set points, okay, similar to what we saw in the T1100, where we'll be able to choose with our demand what we're going to target for a discharge air temperature. And that will just be a sliding scale versus if we were using the staged output on this and we go set up our summer, we just basically have when do we turn on stage 1, when do we turn on stage 2. Okay, so very simple, same output, no wiring changes there, just additional electrical capability on that. So, okay. Now focus, and this is something that people have been asking for a long time. It took us a while to engineer. But you now have the ability to walk up to a job that you have never connected to before and do a complete network discovery of every single controller that is on the entire network. Previously, you could discover everything as long as you knew all of the addresses of your masters, but now we don't even need to know that. We can connect. Just connect to a NC2000 or just plug in on a network even if we don't have one and go find everything that is out there. So that will look like this. I'm going to go and connect to our demo board. You're aware of our demo board that we have available for you guys to connect into to try things out. So I'm going to use that right now. Okay, so at the moment it's finding a bunch of stuff that it doesn't like because of all of my other controllers on there. We're just going to delete everything. And I'm going to come in with a blank project. Okay. I was having problems with our demo board earlier up there. Okay, I have a backup plan. So what we're going to do instead is we're going to connect to my little demo board right here sitting beside me. It's slightly more impressive with the larger system. But now that I'm connected, I just go to Options, Synchronize, and Discovery. Okay. One thing to note is if you have any controllers out here, if like you know some of the controllers and you've already brought them in, everything will be deleted. We are going to completely wipe the entire project as you have open. So maybe you want to do this in a fresh, clean project. Okay. Because once we tell it okay, it's going to wipe everything out. At this point, it is going to scan every single address. Now, when it does actually find an address, it goes much quicker because as soon as it gets an answer back, we're on to the next. So a more populated network is actually going to scan faster than a smaller network. We're able to move about 2 controllers per second. All of these addresses, I can tell you there is nothing at these addresses, but we have to check every single address along the way. You'll see once we hit 99, it's going to skip real quick because it'll go across the network controller and it'll get a response there. So we just hang here, wait for it to get all the way to 127. Once we get to 127, it will bring everything in, refresh, update all the controllers, and our focus will match what we're connected to. So we found a master at address 3, so we're getting the list. So there everything came in. Everything's all synchronized. We found a total of 4 devices. So I've got 3 of them here. And if I go up to my global level, here's my network controller. Okay. So that was our, I just want to try this one more time. See if it will connect. Oh, it did connect. So let's see how this looks. Okay, see how stuff's going a lot quicker. And here we are. So this is that demo board that maybe many of you have played with. We're synchronizing all of our systems, pulling in all of the individual controllers, refreshing everything, 17 devices. See how quick that went? And we can go open up and see our rooftop. Here's all of our separate zones. So that's going to be a pretty handy feature if you walk into a building that you've never been in before, coming in behind a different contractor, or for whatever reason something got lost. Okay, so now last but definitely not least, we are going to move over to the Flex IO. So this is our most substantial update. We have a whole series of new input types. This is not the complete list of inputs. These are just the inputs that we've added. I'll show you those in a little more detail when we get into the controller. So we've added a new current input range, 0 to 20 milliamps. It doesn't happen often, but it can happen. Previously, we could only bind to another contact-based output or an output, whether it was on or off. And so if we needed to bind really to an input, logically we had to sacrifice an output for that binding. I can now bind directly to a contact-based input. We also now have customizable analog outputs. So we can create weird analog output ranges, 6 to 9 volts, 3 to 6 volts, stuff that doesn't fit into a 0 to 10, 2 to 10, 0 to 5, 1 to 5, those types of outputs. Okay. Now, as you are well aware, anytime we say ProLon and temperature in the same sentence, it means 10K type 3. On the Flex IO only, now, we have the ability to accept linear transducers for some specialty applications. So that will take a 0 to 5, 1 to 5 volt DC, 4 to 20, or 0 to 20. Places that this can come in handy, I have seen some applications where we wanted to share a value from one flex to another flex because of all the logic. That it was so complex, it took 2 flex IOs to handle it. But we wanted to work off of one common temperature sensor rather than multiple temperature sensors. So this could be used to move an analog output to an analog input on another flex, or like I said, a linear transducer. We also have added virtual outputs. The M2000 hardware gets 2, the C1000 gets 5. You might think that's a little backwards. Well, the M2000 is more capable. Why doesn't it have more? Well, with all of the logic that we've added in here and capability, we are approaching the limits of the M2000 as far as memory capacity before we have to restructure everything in order to fit more in there. But basically, these virtual outputs, they are just exactly that. I can create an output logic, whether temperature or state or whatever based, and I can just use that for binding to another output. Okay, you now get a set point reset. Okay, so I can do a linear set point reset. I can do a state-based set point reset, occupied, unoccupied. So I can change my set points based on yet another input rather than having fixed set points. We added a backup output. So we now have a second controller that can do lead lag rotation, exercise functions, failover. Okay, our mindset when we created this, of course, was pumps, but you could use this with anything. Basically, it's going to be an output that's going to be joined to an input to prove that output, and then we'll put 2 of those sets together to work in a pair for handling one single function. Okay. We also have on our contact inputs, we've added a hold and a toggle. We'll cover these here, but some potential uses on this would be like an override button for a lighting control. If we were going to use a Flex IO for schedule-based lighting control, and I needed a momentary contact button on the wall that employees could go push, and when they push that button, they get 2 hours of light. So we have a lot to cover here, so I'm going to go ahead and move into focus on this. And we can disconnect from this guy, and we will just clear everything out. So let's just go here and get a flex. We will work with the M2000 hardware, so just the most capable. So as you can see, the icon hasn't changed. Only difference, we do have a 4th line available for icon information. Previously, we were limited to 3 lines. When we open this up, everything's going to look very much similar, except when we get down here in our network inputs, we've got everything that we're used to: outside temperature, supply temperature, math functions. Remember, this is all stuff that can be coming from a rooftop. Okay, but I now also have fan status. Okay, so I can pull the fan proving from the rooftop to use as an interlock point. Say if I was going to use a flex IO on a hot deck, cold deck system, I'm going to have my rooftop control the cold deck aspect, the fan, the cooling, and then I'll drive a hot water valve, possibly reset off of a math function or outside temperature, but I want to make sure that my fan's running before I go opening that valve. So I'll be able to bind to that. So let's head into the inputs here. Here's our temperature. Normally, we're going to be this 10K type 3, but here's where you can choose all of our inputs, 0 to 5, 1 to 5, 4 to 20. We have that 0.5 to 4.5 for some special transducers that decided they needed to use that. And then 0 to 20 milliamps, that's our new current in there. Contact, still have the same, it'll display as open, closed, on, off, yes, no. Default is what you're used to. The input is on when the contact is closed. Hold, okay, so this is where momentary contact is going to cause this, if I were to put 20 minutes in here, just a momentary closure of those contacts, logically in the controller, this input is going to remain on for 20 minutes if I were to do this. I also have the option to call this a toggle. So with the toggle, basically I have, using this fail-safe delay, it's the same as that hold where I'll drop out after 20 minutes, but say I only ended up needing it for 10 minutes. Well, if I go push the button a second time, a second contact closure on this will toggle it off, okay? So possible uses for that with lighting control. Okay, now we start into our linear measurements. So we still have the pressure, inches, water column. Remember, your first number can always be negative if you're using a bidirectional transducer. Still have the whole selection of signals. So let's just run down the inputs real quick. We have inches, we have PSI, pascals, gas concentration, parts per million, parts per billion. Humidity, check this out. Humidity is now scalable. It used to be just 0 to 100% across our analog signal coming in. But some of the precision 1% accuracy transducers that we are seeing, especially now in the, we'll say, a certain grow industry that is taking off in various parts of the nation, they're using high accuracy transducers. They'll only look at a 40% range. So I can say, well, I want to see from 40 to 80%, or 30 to 70, depending on that particular transducer, whatever they've chosen. Okay. Voltage, obviously, you're going to have a transducer for this. You're not landing high voltage to the controller. Current, amps, milliamps, frequency, so you can get feedback out of VFDs with this. Kilowatts, flows in CFM, GPM, liters a second, velocity, speed, level. How about this? Level, transducer, think tank level sensors. You put the little transducer at the bottom of the tank, and it's going to tell, how many feet of liquid is in this tank based on the weight of it. So you can use this for an autofill or a pump to ramp that pump up and down. Percentage is scalable. Okay, well, why would I want anything other than 0 to 100%? Well, thought process on this was having accessibility to LEL sensors, propane, natural gas, Okay, full scale on a lot of these transducers is 0 to 50%. So that way I can show this as propane LEL and have, it's going to display a range of 0 to 50% across the full signal. We don't want someone thinking, oh, I've got 100%, we're about to explode. So that's why we can scale that. And then last but not least, I've got a no unit. So if nothing else I had here was good enough for you, it just didn't fit what you needed, we're just going to take this range of numbers and scale it across this signal, and then it'll be up to you to provide a name that's going to mean something to you for this. Okay, so let's just do a little exercise here. I'm going to build a chiller controller. Okay, we don't have a chiller controller yet. We're just starting to work on that, but I can build a fairly respectable chiller controller using this setup. So I'm going to have a temperature input, and we'll just do chilled water supply. I can grab another one for chilled water return. Now, obviously, to go with this chiller, I'm going to have a couple of pumps. So we can have chilled water pump 1. Now, look at this. This is inputs. So I just want to use this to prove that my pump is running. So chilled water pump 2 flow, and then these, of course, are going to be contacts, and we'll say yes, contact, yes. We'll leave those in the default operation because we don't want them doing anything other than what their immediate state is. And then we can also throw in here pressure PSI, chilled water pump pressure. Just say this is maybe a 0 to 50 PSI on here over maybe a 4 to 20 milliamp. Okay, so we've got a few good inputs here. Let me go grab a digital output. Okay, outputs are going to be the same on here. I've got my local input, network variable, occupancy. We'll get to this back up in just a minute here. So local input, chilled water supply. I want to have this control my chiller. We'll use a set point of 44 degrees with a cooling differential of 4 degrees. Differential action, if we hover over that, we'll see that we're going to split our differential 50-50 either side of our set point, just as we normally do. Okay, just like that, I can say, well, if outside temperature is less than 32, turn this guy off. If we're below freezing, I don't need to run the chiller. Okay, so this was kind of where we were limited before, okay, because I'm using a fixed set point, but I can do a reset on this, and I could do my reset based on another temperature sensor. I could base this off of my return. I could base this off of a network variable. That network variable could be outside temperature. So the hotter it gets outside, the colder my water is going to get. I could base it off of a math function that's maybe looking at a cooling demand. The higher the demand, the colder it's going to get. Let's just keep it simple here. We'll stay with outside temperature, and we'll say that, well, if we're 40 degrees outside, I want 55-degree water, but by the time I get to 80 degrees outside, I want 42-degree water. Okay, so what will happen is this will slide as a linear scale. We're still going to apply the same differential to whatever our calculated set point is on this. So there, I've got my chiller that will enable based on a sliding scale from outdoor air temperature. Okay, to go with this chiller, we've got those pumps, remember? So we're going to step into another output, and we'll have this run off of occupancy. I realize this might not be how we do it in the real world, but just for demonstration purposes here, this will be chilled water pump 1 output on when occupied. And I'll say if outside temperature is less than 32, turn this guy on. Get that water moving, give me a little freeze protection. Okay? So here's output 1, and previously I had to have, for my chiller, I could say deactivate this when chilled water pump 1 is off. The problem is I'm binding here to a command. I'm binding to an output. I've told my pump to turn on. I don't know that it did in fact turn on. So we will now see in this binding list, remember those contact-based inputs. And of course, I still have fan status. That automatically shows up in everything. I'm not going to care about fan status on this, but I can say, well, chilled water pump 1 flow is no. Don't let my chiller run. Okay, but we have the situation here of our 2 pumps that we need to lead lag rotate. So I'm going to choose yet another output. But this output, I don't want to base it off of occupancy. I'm already looking at that. I don't want anything else. I'm going to use this output to back up another output. So we're going to select backup here. And my source output to back up is going to be chilled water pump 1. Okay, so any output there, we can choose how we're backing it up. We're backing it up with chilled water pump, fat fingers today. Chilled water pump 2, activate backup if source does not prove. This is very generous. I'm not so kind. I'm going to give it about 12 seconds to prove. Okay, lead lag, same rotation strategies as before. Alternate after each call, fixed runtime, you choose your runtime, and equal runtime. Remembering again that equal runtime does require us to satisfy and to shut down this output, okay? So proof of the source output. What is the source output? Source output is chilled water pump 1. How am I proving that? I'm proving that with chilled water pump 1 flow. Proof of this output. This output is chilled water pump 2. How am I proving that? I'm proving that with chilled water pump 2 flow. Now, say if I don't have individual proving, I've got a common flow switch after the pipes come back together, it is just fine to have these proven by the same source, okay? So, but we'll use separates here. Here's your exercise option if you wish to take advantage of that, okay? Here's another feature. Allow both outputs to turn on if backup fails to prove. What is this situation? Okay. Pump 1, you're up. I need you to turn on. Pump 1, okay, pump 1 failed. Start pump 2. Uh-oh, pump 2 did not prove either. Both of my pumps failed. If I have this box checked, my controller is then going to turn on both outputs and just hope that something is happening. So smaller circulator pumps, little hot water circulators or something like that, we can get away with this and just hope that something is moving. Some larger pumps, where each pump is capable of the full capacity of the system, we might not want to turn on both pumps because we could be overpressurizing and overdriving stuff. So that's why we give that as an option here. So I have my I've got my pumps on this. We have our lead lag rotation set up. So pump 1 and pump 2 will work together with lead lag rotation with failover safeties. But we now have the issue of, well, if I'm going to my chiller, well, if I'm going to deactivate based on chilled water pump 1 flow, well, what happens when pump 2 is the lead? Because 2 is going to come on, it's going to prove, but if pump 1's not running, if I don't have flow proven on 1, my chiller won't be allowed to run. So this is where our virtual outputs are going to come in. So we look in our config list here. Now we've got digital, analog, and we have virtual. So we'll go here to VO1. And everything about this output is exactly the same as any of my other outputs. The only difference is that I do not have any physical hardware that is putting out any kind of electrical signal or voltage in conjunction with this particular output. If I choose an input that is a temperature, I'm going to have a temperature-based logic for this. The output is exactly the same. I still have the same bindings and overrides available for my virtual outputs. Okay, so I'm going to create an output here. It's going to look at chilled water pump 1 flow, and I'm just going to call this flow interlock. And what I'm going to do is this output is going to turn on when my contact is closed. So if chilled water pump 1 flow is proving, that's going to turn on virtual output 1. I can now use my binding feature here to activate this output when chilled water pump 2 flow is yes. Okay, of course, since this is interlock, again, I want it to be actual current state. I don't want to override for any reason whatsoever. So if you look at what I've done here, a contact input from chilled water pump 1 flow or from chilled water pump 2 flow, either one of those will cause this flow interlock virtual output to quote unquote turn on. I now can go back to my chiller here and find in my output binding flow interlock. So I will deactivate my chiller in the event that my flow interlock is off. So see how I put that together? I still have the ability to go and set up a analog output. We still have that pressure transducer we're looking at. So we're going to look at a local input based on my chilled water pump pressure. And this will be chilled water pump speed. Okay, we could have, excuse me, we could have our set point of 30. We can have a reset. Okay, again, this reset could be based on demand, temperature. Okay, if we based it on occupancy, okay, I can have an occupied set point, an unoccupied set point. So several different strategies there. And then as far as the hold and the toggle, let's go grab another input. And we're going to call this guy lighting override. We'll give this a hold feature on here when it's not really going to apply needing to show this other than to verify that this timer is running. So we'll set it up for 60 minutes. And how this would be applied is I would have a digital output that is going to be based off of, say, a network variable. And that network variable could be one of our occupancy slots. And this would be store lighting, output on when occupied. And then I can also say, well, activate this output when lighting override is yes. Okay, so if occupancy slot 4 is commanding my store lighting to be on, well, my lights will be on, and they'll turn off when occupancy slot 4 says turn off. But if we're off and somebody comes and pushes the override button, that will activate this output for the duration of whatever we set our timer to right here. And then just to restate, we have the toggle feature in here, which would allow us, you know, anytime before this expires, we can go push that button again and it will cause it to turn off. Now, one note on the logic with both of these. So say I were to install a light switch as my contact input. So I turn that light switch on and I walk away. After 60 minutes, even though I still have electrically, I have maintained contact, in 60 minutes, this input will drop out. So we did it that way for some kind of off-label features. We can use this for creating delays for like a damper opening delay. We could use this for and get feedback off of an end switch on a damper for operating a fan. So just some different possibilities there. Really, we have a lot of new capability on this. So at this point, I haven't seen any questions come through on the chat. I apologize. Let me pull that up here. So I think at that we will go ahead and wrap up here. If you have any questions, please feel free to contact myself, Christopher.Lyon@ProLonControls.com, or you can call our tech support line, 1-877-977-6566. Thank you, everybody. Appreciate you taking time out of your busy day. Looks like we kept this to a nice 1 hour here. And we look forward to seeing you on the next release.